Hello and welcome to this week's string seminar. Today we are very happy to have Sourendu Gupta from TIFR Mumbai, and he'll tell us about emergent long-distance symmetry and the phases of QCD. Over to you. Thank you.
Okay, so this work that Rishi, my colleague Rishi and I have been doing, so this is a kind of progress report, one piece of that. Now, the context is the following. As many of you may know, there's, the experiments which produce strongly interacting matter, okay, and there are natural experiments, neutron stars, where probably you see similar things, and all these things start off equilibrium, and then they gradually come to equilibrium. Okay, so we really have to understand the dynamics of this hot matter. Okay, and we don't have good non-perturbative methods for that. Okay, so but first we want to therefore figure out whether we have a good description of the equilibrium system, and that's because the equilibrium system can be pretty well simulated using lattice methods. Okay, so from lattice methods, what we know is the kind of phase diagram with as you change these free parameters, the masses, the light quark masses, and the strange quark mass. Okay, the strange quark mass is much heavier than the light quark mass, so I have inverted the axis so that for the strange quark mass, infinity is at the origin. Okay. Now, what we know about this system is that at finite temperature, there's a phase transition in the chiral limit where the light quark masses go to 0, okay, and the strange quark mass is large, okay. There's a phase transition, a critical point at each strange quark mass, okay, as the light quark masses go to 0 and you scan in temperature, there's a critical point, okay, so there's a critical line on this figure, and that belongs to the O4 criticality class. Okay, that of course you can, you know that from universality arguments, just symmetries, and you also know it today by direct lattice calculations which take this limit. Okay, so that's what you know, and you would like to have some other way of doing. Now, the lattice computation cannot probe of equilibrium dynamics. Okay, so you want to have some other way of describing the same system so that you can use those techniques. You can use, for example, quantum field theory techniques to look at the off equilibrium dynamics of this. Okay, now when the temperature goes to 0, you have various quantum field theories that you can use. There's, of course, one good starting point, which is an ideal resonance gas. And there are hadron EFTs that you can use as the temperature goes to 0. Okay, and they are very well tested in hadronic physics. You can take the chiral limit of that using chiral perturbation theory, and everything works. So you know how to do this at low temperature. You could use these theories here and find out what they say about the off equilibrium dynamics of this system. At very high temperature, you can use weak coupling expansions. Okay, weak coupling expansions work well for the thermodynamics, and there are no indications that anything goes wrong with them when you use them to look at off equilibrium dynamics, close to equilibrium. Well, not very far off equilibrium perhaps, but close to equilibrium dynamics. Okay, what we don't know is what happens close to this critical point or the crossover at finite mass, okay? And that's the region that we have been looking at, the two of us, using thermal effective field theories, and I'll explain what that technique is, okay? What we have been doing in quite a great amount of detail is to make sure that they correctly describe what we see in the thermodynamic limit. But these are effective field theories, quantum field theories. So once we have them calibrated, and then we should be able to use them to say something about the dynamics of the system. Okay. And maybe if I have time at the end, I'll say a few words about that. Okay. So what do we know from the lattice calculations in equilibrium? Okay. We have, we can begin to plot the, plot things like what I showed earlier. Okay, where are the critical points? Where is it phase transition? Where is there no phase transition, and so on? Okay, so this is called the Columbia plot. It was first drawn in 1990 based on 3 different simulations. It's been, the state of the art has improved considerably since then. And this figure shows what was conjectured then, that along this line, where the strange quark mass can be anything, but the light quark mass is small, 0, there's a second order transition. That's the O4 transition that I showed you in the previous picture. Okay, and the conjecture was, and still is, that when you make the strange quark mass light enough, okay, then it turns into a first order transition. So if you come from somewhere here, okay, along a line like this, from some arbitrary strange and light quark masses towards this origin, then you pass a mass where you have a critical point. Okay, and this is, at this point, arbitrary UD quark masses, arbitrary strange quark masses, you don't have O4 symmetry. O4 symmetry is a chiral symmetry, as I'll argue later, and probably already know it. Okay, this you don't have at this critical point, so it's some other critical line. Okay, so along for a certain trajectory of masses, you have a critical point in the phase diagram. Okay, and that critical point, there are no.
I'm not able to see what you're pointing at, but the statement is that the bold line, both on top and below, is a second order phase transition. Any right. Bold line?
Yes, any bold line is a second order transition.
Okay, thank you.
Okay, so, and this curved bold line, which encloses the origin, the first order at the origin, is supposed to be a Z2 symmetry, okay, Ising symmetry, okay. And here there's a point where the Z2 symmetry line meets a O4 symmetry line, and that's therefore some kind of a higher order criticality, perhaps a tricritical point. Okay, when you go off towards very large masses, then of course you get to the pure gauge theory, where there's a completely different order parameter. It has nothing to do with chiral symmetry, okay? And, you know, there's a first order phase transition. I'll not talk about the high mass region at all, okay? Most of the interesting physics is in the low mass region, so I'll just concentrate on that. Okay, so I'll try to set up EFTs, effective field theories, which we can use, okay? And I'll try to set them up at finite temperature, okay? They'll differ from the things that we know at 0 temperature. And what I'll do is, these EFTs will incorporate the symmetry and the symmetry breaking that we are going to look at. That's the chiral symmetry of the quarks, okay? And since we are talking about an effective field theory, not a UV complete theory, therefore there'll be a UV cutoff in the theory, okay? Where should we put that UV cutoff? There are lots of masses when you look at the hadron spectrum, right? The lowest masses are the Goldstone bosons of this chiral symmetry breaking. And that's the pion, the kaon, the eta, and so on, okay? And then there are the vector mesons, then there's the baryon, okay? Maybe the vector mesons are actually resonances which couple strongly to the pions, okay, or the kaons. So they should not have independent identity. In any theory of interacting Goldstone bosons, you should be able to generate those out of the interactions, okay? So I don't think they put a bound on where you can put the UV cutoff. But certainly, the UV cutoff should be less than the baryon mass, okay? Otherwise, you'll have new physics, which has to do with baryons, okay? So if I want to see only the physics of the phase transition of the Goldstone bosons, then I have to put the cutoff somewhere lower than the proton mass, okay? If I just want SU2 theory, then I can push it down all the way to the pion mass, so anywhere in between. But if I want to keep the strange quark in the game, then I should not push it below the Ka atom masses. Okay, so there's notionally a cutoff for the 2 flavor theory somewhere here, and a 2+1 flavor theory somewhere higher. Okay, so you choose the cutoff, you choose whatever you need to do, and you start writing the effective field theory. Okay, but that requires you to understand the symmetries. Okay, effective field theory is basically built from the symmetries that you expect.
Would you keep eta prime, or would you keep eta prime, or would you put the cutoff before that?
We can keep the eta prime. Okay, so I'll come to that. Okay. So first thing, the space-time symmetries. Okay, we are talking about finite temperature, so the space-time symmetries are going to be not exactly the vacuum symmetries. Okay, the symmetries that you expect when there's no matter around. Okay, there is matter, there is thermal matter. Okay, there are Bose and Fermi distributions which describe this matter. Okay, and the Bose and Fermi distributions have simple expressions in particular frames, in a particular frame. Okay, so there's, you can in general go from one frame to another using a time-like vector u. Okay, and in an arbitrary frame, the Bose distribution would be something like this. The Bose distribution for a particle of momentum, 4 momentum q, will have this form, okay, but with this functional dependence on u dot q. Okay, so there's an extra vector in the problem. The symmetry has to respect that. Okay, so what you have instead of full Lorentz symmetry is the little group of u. Okay, that's the remnant symmetry that you need for your EFT. Okay, and that's a time-like vector, so you can always choose a special frame which has u equal to 1 and 0 for the spatial components. Okay, and in this special frame, this little group is, you can see it's nothing but the rotations orthogonal to u. Okay, and of course the CPT that came from the fact that you had you started from a Lorentz invariant objects. Okay, now this is, of course, looks like a non-relativistic problem, and that's kind of important to the structure of the EFT. But the EFT is still fully relativistic in the sense that particles can be relativistic. Okay, the whole matter has a special frame, but particles inside the medium can be relativistic. So the dimension counting that you have to do for OPs, okay, there will still be the relativistic dimension counting. Okay. So what are the possible terms that we can now write down for our effective field theory? That will depend upon how we implement these symmetries. Okay, the symmetries are the space-time symmetries that I showed you, and the chiral symmetry for the given number of flavors of quarks. Okay, so what are the fields that we choose? We choose to implement these chiral symmetries, these symmetries on fermion fields. Okay, these fermion fields are more or less the quark fields. Okay, only they're long distance fields. Okay, and here's a crucial assumption that I make. Okay, and this assumption is not something that I can prove, but I can test the results that follow from this assumption. And the assumption is that at long distances, these fields that I have, the kind of long distance versions of the quark fields, have no color interactions. Okay, so what that means is that I'm talking about the gluonic degrees of freedom, even though I'm at finite temperature, and maybe the glue balls are gone, I'm still thinking of the gluon degrees of freedom being gapped. Okay, so I don't have to take into account the gluon degrees of freedom when I go to low energy. Okay? This is a problem, of course, when you are in a phase that is more easily described in terms of quarks and gluons. Okay, when you're in the low temperature phase, then there might still be glue balls. So this is a simpler argument. But okay, we take this argument. Okay, at the moment we can't prove this one way or the other. So then what are the terms that we can write? We can write a dimension 3 term psi bar psi with a coefficient which is the mass. Okay, the coefficients, I'll use the cutoff lambda, okay, explicitly so that the coefficients are given as dimensionless numbers. So this is the D3, you can think of it as quark mass divided by lambda. Okay, it's a dimensionless number. The dimension 4 terms are the kinetic terms, okay? And if you had a completely Lorentz invariant theory, then it would just be give you the Dirac equation, right? But here we don't have Lorentz symmetry. So in this particular frame that we choose, the frame in which the overall center of mass of matter is not moving, okay, I have two terms. One is the time derivative term and one is the spatial gradient term, okay? And they can have independent coefficients, okay? So I'll choose the renormalization of this long distance field such that the time derivative term has the canonical coefficient half, okay? In which case the other coefficient is free, okay? Already this gives you something new, okay? If you just had a Lorentz invariant term here, then the dimension 3 term and the dimension 4 term together would tell you that there's something called the rest mass of a particle, okay? And that's the only characteristic of the particle, okay? But here, because that symmetry is broken, okay, if I take the spatial momentum going to 0, then the poles of the propagator will be at what we call the rest mass, that's D3 lambda, okay? But if I take the static fields, so that the time derivative is 0 and momentum can be anything, spatial wavelengths can be anything, then I get something which is different, okay? And that expresses the fact that in matter, charges can be screened, okay? So they are screening masses, okay? The rest mass and the screening mass are different. So, yeah.
I just want to clarify, when you say the quarks are color bleaks, that means in these terms, there's no color index for
Yes, that's right. There are no color indices, or you can put color indices. Actually, I've put color indices because I want to do the NC counting, okay? But the interaction terms have I mean, they just contract the color. If you put a color index alpha on psi, then it has to contract with a color index alpha on psi bar.
Okay, so there's some overall factor of some degeneracy factors.
Yeah, right. So I'll put the dimension of the field dimension contains NC. Okay, and I put that just as a bookkeeping device because whenever I get something, I want to see whether I've got the correct large NC limit or not.
Yeah, and therefore these del slashes that you have don't have any connection or anything like that. There's no glue-on field.
There's no glue-on field at all, no.
Okay, thanks.
They follow the same Clifford algebra, but under the space-time symmetries, they break up into different groups. Okay, so this D0 slash has a gamma 0 d by dt, and the nabla slash is gamma I d by dxi. Okay, the Clifford algebra is still the same. We have the same Dirac. Okay, and that's exactly what happens when you come to the next term, the interaction terms. Okay, if you were to write these interaction terms with full Lorentz symmetry, then you know that these Dirac structures, this is not just a Dirac structure, this is a Dirac cross flavor structure. Okay, but the Dirac part of that structure could only be scalar, pseudoscalar, 1 gamma 5, okay, gamma mu, gamma 5 gamma mu, and the tensor. Okay, that's not true anymore. Each of these things can break up into multiple pieces. So for example, the vector gamma I will break up into one piece which is gamma 0, okay, and another piece which is all the gamma i's. Similarly, the tensor, the 4 tensor, will, the rank 2 4 tensor will break up into a rank 2 3 tensor and something else, right? Which is like an axial vector.
One question. So usually when we do low energy thing, we just use chi-PT, right? Which is just, you keep the Goldstone bosons and the scalars basically. But you want to keep some fermions.
I'm implementing it on fermions.
Yeah, but is there some reason you want to do it?
Yes, because if possible, I want to go across the phase transition.
Okay.
Okay, so in one phase, I should be able to see the fermions as the long distance field. Okay, so that's the reason you took.
Yeah, so, and the statement, the fact that you don't observe these at low energies, you model by saying that the mass term is like lambda. Is that
No,
the point?
mass term is d3 times lambda, but you want to see the chiral limit also. So you could push d3 to 0.
Okay.
Okay, so we will see, it's a phase transition. As you change the temperature, you have a phase transition only when d3 is 0. Okay, that's the only place where there's a sharp transition. Okay, the degrees of freedom on one side could be different from those on the other side. But it has nothing to do with confinement or deconfinement. It has to do with presence of Goldstone bosons or not.
Yeah, the thing that confuses me is that if you just come from low energies, and if you just look at the free energy, let's say, so you might think that it is just the
Low
ideal,
temperature.
Yeah, low temperature. Yeah, low temperature. Then you would think that you would just get first the ideal gas of pions and so on.
Yeah.
You won't see the ideal gas
trouble
of this
with
size.
that is you won't see the screening. If you start with the zero temperature theory, then getting the screening is totally non-trivial. Okay, and it has to do with the microscopic stuff that you don't want to keep track of in this approach.
But would this theory have the same low temperature free energy?
It should, okay, it should, but it will be non-trivial because the low temperature, this D4 should go to 1. Okay, or in other words, if you start with something at low temperature, then you should be able to get you should be able to compute D4 if that's more UV than this theory. Okay, we can talk about this later. Okay. So anyway, so if you go to, so there are no dimension 5 terms, that's ruled out by CPT. Okay, then you come to dimension 6, there are these 4 Fermi terms. Okay, and then there are higher derivative terms with which modify the kinetic term. Sorry? Yeah, it will contract, sorry, thanks. Yeah. Okay, and if you count the number of different possible gammas, capital gamma structures that you can have, flavor cross spacetime, okay, flavor cross Dirac, then you'll see that there are 10 of them. And, these coefficients D6i that I have, okay, these dimensionless coefficients are therefore related by chiral symmetry. Okay, and there's this term, okay. Now, one of the things that, one of the answers to what Loga was asking is that you can see that this is very similar to the NGL model. Okay, the NGL model will just take a gamma 5 times flavor matrix and a gamma 1. Okay, just retain those two things and work with it. And that, of course, gives us the overall structure that we know about the phase transition. Okay, so now why do I want to do more? I want to do more than that because I want a full EFT. I should be able to expand it, go beyond the NGL, go to higher dimensional terms if I want, and so on and so forth. Okay, so we want a full effective field theory and not just a model where I pick some of these coefficients and drop the others. Okay, so for example, the NGL model does not contain these terms. Okay, so that's one thing. But when you see a 4 Fermi structure like this, then you also ask yourself, where else can I get it? And one place that you will see 4 Fermi structure is the low energy limit of electroweak theory. Okay, so if you look at electroweak theory at finite temperature, and that could be important in the early universe, for example, then you should be able to write a similar expansion for the, let's say, the electrons. Okay. Then the lambda, the cutoff lambda, could be anywhere between the muon mass and the electron mass. Okay. So you want the electrons in the theory, but you don't care about the muon, so you put the cutoff lambda somewhere there. Okay. But you know that if you're working at temperatures below the electroweak symmetry breaking scale, then there are even higher masses, MW, MZ, and so on. Okay. Now, so you can, in that case, you can simply calculate these things. Everything is perturbative. Okay, so you can simply calculate these coefficients D6, D4, D3 in perturbation theory. Okay, and then you see that they're all non-zero. But this D611, for example, turns out to be down by powers of the W mass. Okay, so that's why if you look at electroweak theory at finite temperature, you don't really have to take this into account. It doesn't, I mean, in principle it's there, but it doesn't make any numerical difference. Okay, and you also find that, you know, you get some corrections to the usual 4 Fermi theory, okay, at finite temperature, but you can calculate all that and it's, okay. So there are various ways you can use these models. Now we took the two-flavor theory some years back, 4 or 5 years back, okay, and we went ahead doing all the textbook stuff, okay. We constructed the mean field theory. When we construct the mean field theory, we found that all these 11 different terms do not enter separately. Only a particular combination enters, which we call D6. Okay. So then that's why the mean field theory looks a lot like the NJL model, where also you get only one coupling. Okay. And you know, so the overall physics looks the same, but of course the numbers change. Okay, so then after that, after we do the mean field theory, we introduce fluctuation fields, then we integrate over the fermions to keep only the fluctuation fields so that we don't do double counting. And these fluctuation fields are just the Goldstone bosons.
Yeah. Sorry, Sourendu, maybe I'm misunderstanding something. But is this mean field, is this effective field theory also supposed to capture the phase transition? Is there?
Yes, it's supposed to.
I see. So it's and that's a pretty complicated, and you will explain how that happens, or?
It happens the same way as it happens in the NGL model. As you see, the mean field theory, there's only one of the combinations which enters. So if you did the mean field theory for the EFT, it wouldn't differ from the mean field theory that you do for the NGL model. Okay, so it's just the usual textbook thing.
I see.
Okay, what we gain here is that the numbers change, the actual numbers that we have change, and therefore we can describe QCD more accurately. Okay? The mean field theory does not change. Okay. Okay, so the Goldstone bosons, the theory of Goldstone bosons, if you write down all the, again, you do the same thing, you can write down dimension by dimension, then there's a dimension 2 term which has the mass of the Goldstone boson, which is 0 if D3 is 0 in the chiral limit, but otherwise there's a mass. Okay. The kinetic terms break up into 2 pieces, the time derivative and the spatial derivative terms. Okay, and there's a coefficient here. Okay, and then there's a dimension 4 self-coupling, 5-4 term. Okay, and its coefficient also goes to 0 in the chiral limit. If you remember, Goldstone bosons are not coupled, are coupled only weakly to themselves, right? And that's this lambda pi, the self-coupling vanishes in the chiral limit. Okay. But now we have a UV theory from which we get this. The UV theory is the effective theory that I had given you before. Okay. So I can compute m pi, u pi, lambda pi in terms of the parameters in that theory. And there were 3 parameters in that theory. D3, which is the quark mass. D4, which was this kinetic, the screening term. Okay. And D6, which was the coupling in the mean field theory. Okay. So in terms of those, I have these. Okay. Now I can use this theory to higher accuracy. I can do all kinds of fancy things. resum the pion propagata and so on. Okay, what does that gain us? That gains us the ability to use lattice measurements of pions at finite temperature to get the couplings of the fermionic theory. Okay, pions are easily measured on the lattice. Okay, so there are lots of measurements. We use those to fix our theory, right?
Okay, so sorry, I forgot. What was the reason behind having only one parameter from out of 11 in the? I mean,
there were 11 parameters in the mean field theory. It became one parameter
only for this special case.
And these are fluctuations about the mean field theory. The Goldstone bosons are the fluctuations about them.
Okay.
Okay, and this is accurate except at the near the chiral critical point. At the critical point, you'll have to sum infinite number of pions to get. Okay, so there'll be complications at the critical point.
Okay, thanks.
But as long as the masses are finite, this is good. Okay, so we have done these fits, and here's an example. Screening masses are measured on the lattice. Okay, we put one of the screening masses in, along with two other parameters, which are not in this figure. Okay, and we get the whole spectrum, the screening masses over a whole range of temperatures correctly. The golden band is the 1 sigma that arises from the errors here. Okay. And that's the pion screening mass. The pion pole mass is not measured on the lattice because the lattice is static. Okay, so here is the prediction for the pion pole mass. As you can see, the pole mass decreases as you come towards the crossover. But after the crossover, the pole mass goes up because what you're seeing are not pions any longer, but at high temperature you'll see quarks. Okay, so the pion doesn't exist. Okay. So these are things, more things you can do.
So so here you are, I'm trying to understand, do you have the full SU2?
Yes,
isospin
we have the full SU2, cross SU2 to begin with. We have broken that, okay. And we have broken the axial part, and the vector symmetry is left over.
Yeah, so there's a spontaneous breaking. But explicitly, for example, you don't take into account the difference between mu and md.
No, we don't.
That affects.
We can do that, but we don't.
Yeah, okay. So this is mu equal to md theory. Okay, and here you get so these phi's are all like pions. Three pions, pi plus minus. Okay, and can you just so the pion screening mass is this m pi or here?
The pion screening mass, the pion pole mass is m pi. Okay. The pion screening mass is m pi by u pi.
Oh, because it's the static.
It's the static.
Static pole.
Yeah.
Omega equal to 0. Okay.
Okay. Good. So, right, and we take the SU2 symmetric limit because lattice computes in the SU2 symmetric limit. Okay, so it's then we can directly use the lattice to fix our theory. Okay, the SU2 symmetry breaking is a small term. Okay, so we can do that perturbatively. Okay, if needed. Right. But now we can go to 3 flavor in the same way. And when you go to 3 flavor, you find that there's an accidental symmetry. Okay. In QCD, you have UNF cross UNF symmetry for the quarks. The left-handed and the right-handed quarks each transform under UNF symmetry. Okay. The vector part of this, the vector U1, okay, U1 cross U1 on the left and right, okay, that's baryon number, okay, that's an absolutely conserved quantity within QCD. Okay, so that's always preserved. But the U1 axial, okay, is broken by the vacuum, by instant-on effects actually. Okay, but these do not appear at all up to dimension 6. Okay, if you enumerate the dimension 6 terms and look at the symmetries, you find that it has an enhanced symmetry U3 cross U3. Okay, not SU3 cross SU3. Okay, so one consequence would be that there are 9 Goldstone bosons instead of 8. Okay, that's the eta prime that you talked about. Okay, and how do you get the correct UV symmetry, you have to take higher dimensional terms, and when you get to the dimension 9 term, then you find that that breaks that extra U1 axial symmetry, okay, and gives you back the symmetry that you expect in the UV. Okay, so that means that at low, at long distances, at low energy, there's an enhanced symmetry. Okay, that's what we call emergent symmetries or accidental symmetries. Okay, now is that a bug here in this, or is it a feature? Okay, now in most cases, if you take a arbitrary physicist and ask them, you have got this emergent symmetry, is it a bug or a feature? They'll say it's a feature. Okay, so in the standard model, baryon number conservation is argued long back by Weinberg that it's an emergent symmetry. Okay, the UV theory within which you can, any UV theory within which you can embed the standard model, almost any, has a baryon number violation. Okay, and he explicitly demonstrated which terms violate that. Okay, or you can take condensed matter physicist guy who does graphene and ask them, hey, how did you get this Lorentz symmetry? Does it really make sense? Okay, the Lorentz symmetry of the electron, low energy electron. And he'll say, of course, it makes sense. You know, if you look at electron gas near the Fermi surface, then you get this linear dispersion relations. Okay, so, and we see it. Okay. You'll similarly ask questions about the Hubbard model. In the Hubbard model, there's some, in the long distance, there's some gauge symmetry. There are various kinds of gauge symmetries which arise, and there are also things which have consequences, experimental consequences, observable consequences. Okay. Similarly, if you look at heavy quarks, okay, if you take the non-relativistic limit of the heavy quark, you'll find an extra symmetry. Okay, it's called the spin symmetry, and that actually has consequences for the masses and weak decays. There are spin partners which are singlet, triplet spins, have very similar weak decay constants or masses. Okay, so they're usually emergent, usually bugs, not bugs, they're usually features which you can see in the physics. However, if you looked at the meson spectrum, then the eta prime and the eta are split by a very large amount, and this measure, the difference divided by the sum, is 1/4. Okay, so difference divided by the average would be about half. Okay, that's a large splitting. Okay, so people were very embarrassed by this extra symmetry and said, no, 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 we don't want it. We'll do something else. Okay, but let's forget about the hadron spectrum for the moment. If we had this extra symmetry, what would it predict? Okay, so what do we mean by that? Okay, let's go back and think of the Columbia plot. In the Columbia plot, we didn't have exact SU3 symmetry. We had 2 flavors of light quark and 1 heavier quark. Okay, so let's try to implement that symmetry that in the Lagrangian that we want. Okay, so the only place where the masses actually arise are in the dimension 3 term. Okay, so I have 2 different masses there, a light quark mass D3L and a strange quark mass in dimensionless units is D3S. Okay, the kinetic terms are of course decoupled. Each flavor has its own kinetic term. Okay, so they decouple. The coupling term at dimension 6 doesn't decouple, right? There's a light coupling, there's a strange coupling, and there are terms where there's a light anti-quark gamma light quark times a strange anti-quark gamma strange quark. Okay, so those are these light strange terms. Okay, if you look at this and ask whether this has this extra symmetry, it turns out that it does. The emergent symmetry of this model is U2 cross U2 in the light sector. Okay. So which means that if you take the strange quarks and integrate out the strange quarks, so you had a UV cutoff lambda 2 plus 1 for the 2 plus 1 flavor theory, and you integrate between some lambda 2, which is smaller, okay, and lambda 2 plus 1, integrate out all the modes, which means the strange quarks are gone and the UV modes of the light quarks are also gone. So supposing you do that, okay, then you get an effective lower energy theory, okay, which will then turn out to have a U2 cross U2 symmetry, not the SU2 cross SU2 which I had implemented earlier, but an enhanced symmetric version of that. Okay, so that emergent symmetry does remain. And alternatively, and this is what I'll show in the next slide, okay, you can use the 2 plus 1 flavor theory and do the same kind of mean field theory that we did. Okay, so there'll be a quark condensate, okay, write everything in terms of the quark condensate, okay. Then it turns out that the mean field theory, from these terms, of course, the mean field theories are decoupled. This term gives only a light quark contribution to the mean field theory. This gives only a strange quark contribution to the mean field theory. So the only coupling between the mean field theories comes from here. Okay. But it turns out, and if you do this algebra, that this goes to 0. Okay. Now there has to be a deeper, more simpler group theoretical argument why this term gives you 0 in the mean field theory, but I don't have that. Okay. If any of you is interested, we can talk about it, and you can perhaps give me a better insight into that. Okay. So since that contribution is 0 to the mean field theory, that means that there's no coupling between the light quark condensate and the heavy quark condensate, strange quark condensate, in the mean field theory limit.
Understand. So you calculate some mean field theory and you match it with lattice, and you're saying that that parameter is 0. Is that?
No. If you just do the mean field theory, if you go from the full theory to the mean field theory, then the coupling between the light and the strange quark condensate just vanishes. It's just group theoretical. It's an algebra of the flavor and the Dirac which makes it vanish. Okay. And I can do this algebra and I can see it vanishing, but I can't give you a higher, higher order explanation for this. Okay. Right? Okay. Now when the two condensates decouple, that means that in this Columbia plot that I had given earlier, there'll be two different lines of phase transition. Okay. One will not involve the strange quark mass at all. The other will not involve the light quark mass at all. Okay. So there'll be one along here which does not involve the light quark mass. Okay. And one along here which does not involve the strange quark mass. Okay. So these are two critical lines that we find. Okay. And I'm doing this in mean field theory, so this is my mean field theory Columbia plot. Now you might ask, is my mean field theory completely wrong? Okay. Could these lines not be there? Okay. So then we must look at it in different ways. And people have looked at it in different ways recently. So this is how you look at it. You notice that U2 cross U2, you know that SU2 cross SU2 will give you O4. It has the same number of, same dimension and so on, same topology. Okay. So if you had SU2 cross SU2, that would have given you an O4. And now you have added U1, so you have added an O2. Okay. There's a second one is conserved, so it doesn't matter. Okay. So it's the broken piece of this. The Goldstone bosons of this one are the same as the Goldstone bosons of this. Okay. So yeah, so right. So people have looked at this O4 cross O2. Okay. There have been two independent numerical calculations about 5-6 years back. Okay. One of them takes this as a scalar field theory, okay, in which case there are two couplings, one for the O4 piece, one for the O2 piece, okay, and scanned the phase diagram for different values of the two couplings, okay, and they found that there is a segment of this space of phase diagrams where there's a second order transition and a smaller segment where there's a first order phase transition. So you can have both. Okay. Second numerical calculation used a sigma model with this symmetry. Okay. Only one coupling, and that happened to be a first order transition. Okay. There have been also attempts to do a 1 by NF expansion. Okay. So 1 by NF here. Okay. And epsilon expansions taken to second order, third, 2 loop, 3 loop orders. And the situation is very confused. Different people get different things because they're making slightly different approximations and so on. Okay. So some people get critical points. Some people get multiple critical points. Some people don't see appropriate critical points and so on. Recently, last year, these two people did a conformal bootstrap. Okay. And they found a second order transition for U3 cross U3. But they found a confusing picture when you did the same thing for U2 cross U2, and they say that it depends upon how accurately you try to do this conformal bootstrap. Okay, so in other words, the situation is still fluid, okay, but this mean field lines do not seem to be ruled out. Okay, so this is the Columbia plot that you would expect at least from the mean field theory that we have done. Okay, now that's with the emergent symmetry. Now we break that symmetry. We could take the dimension 7 terms, dimension 8 terms, but they don't break the symmetry. So at the moment, if I'm looking only at the structure of the Columbia plot, I'll ignore the dimension 8 terms. Actually, dimension 7 terms do not exist. CPT rules it out. Dimension 8 terms I neglect for the moment because they don't change the structure of the theory. And I put in the dimension 9 terms. We find that there are 2 of them. Only one has been used before, and that's the famous 't Hooft determinant term, which I've written down here. Okay, it's a determinant in flavor. Okay, and people have computed this coefficient before using some dilute instanton gas and so on and so forth. So they find it to be non-zero. Okay, so if we look at this, what does this tell us? First of all, do the same integration over strange quarks that I had told you about earlier. Okay, now if you integrate out the strange quarks and all the hard modes of the light quarks, then you find that this gives you, see, you take this and let's say you integrate over this pair, C is then the strange quark, okay, corresponds to the strange quark, okay, then you're left with a current-current coupling, right? That's the dimension 6 term that you have already seen, okay? The contribution from this to the dimension 6 terms actually lifts that extra symmetry that you had when you did this without the dimension 9 term, okay? So you get back the generic two-flavor theory, okay? So this does break the symmetry as you expect. Okay. Otherwise, if you look at the 3-flavor limit, okay, and do the MFT, then you see that this would have 3 condensates, right? This would give you 3 powers of the condensate. So it will give you a sigma cube term in the free energy, okay? And with a sigma cube term, you expect that there'll be a first order phase transition, okay? So indeed, there is a first order phase transition. Okay, when all the masses are small enough, then all the quark masses are small enough, then there's a first order phase transition. And you know, you had seen that at larger masses, there's no phase transition. So there must be a critical mass somewhere in between. Okay, so we look at that critical mass. Okay, numerically, we can find, it's just a simple integral, which you do, and you can do it numerically. You find a critical mass, okay? The critical mass is given here. It, of course, depends upon this coupling, the 't Hooft coupling, because in the limit when the 't Hooft coupling goes to 0, then the critical mass is 0. Okay. And we find that over a large range of the 't Hooft coupling, this is actually a power law. Okay. this critical mass goes as this 't-Hooft coupling to the power 3/2. Okay. Now, that's one thing. The other thing that you note is that these masses are rather small. Okay, I've got here 1 MeV. Okay. Typically, pion masses are like 140 MeV. Phase transition temperature is like 150 MeV. Okay, these are extremely small on that scale. Okay, so what is the value of the 't-Hooft coupling that I require to explain the zero temperature hadron, eta prime mass splitting? It turns out to be somewhere in this region. Okay, so if the 't-Hooft coupling does not change at finite temperature, then I would expect that the critical mass is really small. Okay, surprisingly small. But of course, it could change a little, it could drift down or up slightly, but I don't expect it to go up by 3-4 orders of magnitude. Okay, so this is what you expect, that the first order region that you had seen in the Columbia plot is actually very close to the origin. Okay, why do I get these power laws? Why are these numbers small? We can answer that question in, we can control that answer. Okay, so let me just take you through the steps in a broad brush sense, and I'll not give you details here. Okay.
Can I ask one question? So this D9 that you have, can it be measured at finite temperature in lattice?
See, if we, yeah, I could turn the question around. If we measure this critical pion mass on the lattice, then it would be effectively interpreted as a function, as a measurement of the D9.
But do you see but you want to check the phase transition?
I'll come to your question. I'll answer you precisely this question. Okay. But let me first tell you how we get the exponent here and why this number is small. So why this number is small is a little... Okay, so what do? We start with the free energy. Okay, the free energy is given by some integral. Okay, and we show that we can take out a quartic term from that integral and do the analysis entirely in terms of that. So the remainder does not affect the analysis of this within the UV cutoffs that we have given. Okay, so the integral minus this quartic polynomial will have other zeros, could have other zeros, but they're outside the cutoff. Okay, so if we look at the gap equation which comes from this free energy, that gap equation can be decomposed into the cubic equal to 0 and something else. Okay, and that and something else gives you solutions which are outside this cutoff. So this we can prove. Okay, we can prove this by taking upper and lower bounds to that integral and examining what happens. Okay, then we look at the gap equation from the cubic, okay, and ask about the topology of that gap equation. Okay, what do I mean by topology? It's a cubic, it has either 3 solutions, 3 real solutions, or 1 real solution. Okay, which one? What happens when it changes from 3 to 1? What happens is actually that's the point where the number of solutions changes, that's where the critical point is. Okay. At fixed values of D3, D4, D6, D9, etc. Okay. Now, next we find that point where the number of solutions changes and ask whether that depends upon D3 or not. Okay. At a certain D3, we'll find that there's a, I should have actually brought a figure here. Okay, so at some value of D3, that is the quark mass, there's a discontinuity in the topology. Okay, let me put it this way. Okay. And because we are dealing with cubics and so on, we can actually figure those out and write down what are the, how they scale with the different couplings. Okay. Now, what we find is that there's a D9 cubed when we write the critical mass, critical pion mass. Sorry, this is wrong. Critical pion mass. No, this is correct, absolutely. The critical quark mass has a D9 cubed, okay? And there's a sum rule that tells me that m pi squared is proportional to the quark mass. So that means the pion mass goes as D9 to the power 3 by 2. So that we can check from this argument. Why is it small? It's small because the coefficient here is extremely small. Why is this coefficient here very small? Okay, good question. Miracle happens, it just comes out that way. But we understand this number entirely in terms of zeta functions, which give us these powers of pi, okay, the coefficients of powers of pi that go into these zeta functions, and the fact that the spinor that we had taken has 4 components. So the dimension of the spinor has gone into here with some high power, and some coefficients of the zeta function have gone in there, okay? And that has given me this large number here, okay? And if you want to hear more details, I can tell you more details.
The magnitude of the critical temperature.
So TC is kind of half lambda, roughly speaking.
Same order.
Same order, yeah.
So between lambda 2 and lambda 2 plus 1.
No, it's half.
No, when I say lambda, I mean the
lambda.
UV cutoff, which is
UV
between the
it's
pion mass and the kaon.
Yeah, somewhere
right,
there.
Somewhere there.
Yeah. This is in the, yeah. Or in the two-flavor theory, it comes out to be around that, a little higher than the pion mass. Okay. So what I wanted to tell you is that we have a way by which we can get this 3 by 2 power, and we also check that the numbers are themselves very small. So what does the lattice tell us? Okay, so first of all, so here's the Columbia plot. Today, if I were to draw that Columbia plot, I would not draw that large first order region that was drawn in the 90s. I would make it a very small blip out here, okay? And it's very small because the dimension 9 terms which break the U1 axial symmetry are down by 3 powers of the cutoff. Okay. What does the lattice see? The lattice actually cannot resolve this. There have been extensive searches for this critical mass. Okay. In 2+1 flavor, people have taken the strange and the light quark mass ratio to be the physical ratio, and then push both of them towards the chiral limit to search for the critical mass, okay? And they could not find it. They can only find an upper bound, and it says that its quark masses must be less than 12% of the physical quark masses. Okay, physical quark masses, you know, are like 5 MeV for the light quarks, okay? So 1/10 of that, half an MeV. Or less. And this was the state of the art in about 2010 or so. And last year, there was a search along the NF equal to 3 equal masses of the light and strange quarks, that diagonal line, okay? And again, they couldn't find this critical mass. They saw that it is the pion or the kaon mass. Pion and kaon are degenerate, so that Goldstone boson mass has to be less than 80 MeV, okay, at the critical. So it's consistent with what we have seen. Okay, so you can take this as a prediction that it will be of the order of 1 MeV, but if it is of the order of 1 MeV, then lattice will take a decade to get there. Okay, so right now, lattice does not have that resolution to see this. Okay, and this smallness of the critical mass is actually explained by the U1 axial symmetry, the new emergent symmetry. Okay, so I think I'll stop here. My time is up anyway. So there are many questions left, how do you extrapolate this to the chiral limit? As I said, if you want to actually extrapolate the mean field theory to the chiral limit, you should be able to do that, but then you have to sum an infinite number of ion fluctuations and so on, okay? There are ways that we can do that, and that's actually the epsilon expansion. But yeah.
Let's thank Sourendu for a wonderful talk. Questions?
Your analysis seems to depend on these scaling dimension 8 and 9 kind of operators you wrote in the beginning with lots of size, right?
Yeah.
So in statistical physics, often we don't encounter operators with such large scaling dimensions. So how come, what is the main difference between this application and those?
Well, the dimension 6 terms are 4 quark couplings. So those, quartic terms you will have often, okay? The dimension 9 terms are 6 quark couplings. So that would be seen as a 5-6 term in some, So that's...
So the dimension is not the scaling dimension
No,
of the
the
renormalization.
dimension is mass dimension. This, as I said, the theory is relativistic, okay? So the dimension is, there's only one thing that sets the dimension, and that's the mass dimension. So I'm counting in OPE. Okay, OPE is dimension.
Okay, thank you.
Are there questions online?
So any implications for neutron stars? And
well, as I said, yes, there are, all this was done at zero chemical potential though, okay? But the same technique I am able to use in places where lattice does not reach, okay? One of them is at finite baryon density, and the other is finite, real time, Minkowski. Okay, so both are reachable using these methods. So this is actually just a test of this method in a place where the lattice works.
thanks.
Any more questions?
Actually, so this question I was asking, I understand that it is difficult to kind of interpolate to physical pion masses and things like that. But if I just wanted to measure D9 in lattice, is there a way to just do that and see?
Yeah, in principle, see, you won't be able to measure something made of quarks, right? Because you need a gauge invariant measurement. But we could look at pion endpoint functions where this makes an appearance. And if you make that measurement carefully enough, okay, with low enough errors, then you would be able to directly get there. Like I said, from pion correlation functions, you get D6 as well as D3, D4, okay? So the 2-point function, the pion 2-point function does not give us D9, but it should be possible to take a pion 3 or 4-point function to get at that.
Okay. Yeah. But it has not been done, is that?
No, actually, pion self-couplings have not been done because everyone is influenced by this thinking that in the chiral limit, everything decouples. So this is one of the suggestions we have for the lattice measurements, that we measure the 3 and 4-point functions.
Okay.
Equal to 9, there may be more operators as well, right?
Yes, I said that. We have 2 operators. There are 2 operators, not just the Ethoff term.
So that mixing will also be a problem.
Yes. But actually, these predictions I have written in terms of the Ethoff term, but it's actually in terms of the full, yeah.
Okay, let's thank the speaker once again.
Thank you.